So, hello, dear ladies and gentlemen, and let's start our stream. So, the preface to the stream is that I changed finally the window for comments and window for myself, so they will not hinder our eyes to see the text. And another preface. Okay, I don't know what to say else, so let's just jump into the discussion of the article which I announced to discuss. And right now I will show you the article. If it works, yeah, it works. Fortunately, Google Chrome also knows the command which I used to shift the scenes in this studio which I used to do the stream. And that's the main conclusion which I got from the previous stream, that it's better to put here at the top of the chat. So right now everything is better, and if you have some other suggestions what to do better, you can just ask me. Also, I need to click this button in advance. So the article right now is called Configurational Electronic States in Layered Transition Metal Dichalcogenides, which was published in 2019. And it's a little bit related to my PhD. I know some people from this list of authors personally, and several, I mean, maybe once or twice they tried to explain me what's going on here in this article, but it was a long time ago. And currently I have spent around, well, I was counting it intuitively, and it was around like 18, 19 hours. I don't think it was more than 20 hours, how much I was totally thinking about exactly this article. Nothing else, like nothing, not about transitional metal dichalcogenides, not about some cited articles like which use the similar topic. Not about charge density wave, which plays a big role here, but only about this article. Around 18 hours, that's what I was motivated to do, and if there were no such stream, I would be not really motivated to even spend even this time. And right now we will discuss how useful this article is and what is the value of some of discoveries here. Okay, let's jump maybe to the conclusion before someone will drop out of this long stream, which will be maybe for 2 hours. So it's not like idea that we just do some clear statements and pretend that we understand everything. No, that's the discussion stream where we sit without any hurry and just share our ideas. However, right now there is no one in the chat to share the idea, which is absolutely fine. That's not a popular topic, and not everyone who is doing science, I mean, nearly no one who is doing science is working. Okay, very little % of people in even condensed matter community is working in the field of transitional metal dichalcogenides. So it's absolutely fine that no one asks right now questions, but I hope that later the community will grow. Okay, so just to be fair for you, I wanted not only show you the title of the article, but also show you the number of citations so that you can understand how popular this article is. Well, you can judge it how you want. It's not a big number, not a little number also. And also the last preface, what I wanted to say is that these are the people who work for a long time with two-dimensional materials, with some experimental techniques. Some people were developing a lot of theoretical methods. So these are people who know what they're writing, and like there is some authority in these people. So there is definitely a value of the article, but which exactly, that's what we will determine in next 1 or 2 hours, or maybe even more. Okay, so let's open our favorite app, Focus Structure Tool. And here I have several other articles, but they're not really important now because we will be focusing on the article that was announced, Configuration Electronical States. And before we go through each of the sections of this article, I wanted to show you the main conclusion and spend some time on the main idea, because that's the most important thing. And then there is like introduction, which is a very long one, and I was reading it for a lot of time, maybe, I don't know, it took me like 5 hours to went through all of the statements. Then there is a discussion of model. Basically here there is this table of contents, which I mean, so later we will go. So yeah, maybe it's better first to start with the plan, which I have for today. So they have introduction where they discuss just general field of transitional metal Dichalcogenides. They I don't know, they just wrote several pages of different things related to what's going on in this field, and there's a lot of not trivial statements, and they broaden our view, but they are not really giving something new to science as far as I remember. This is just a good collection of different statements. Then there is an easy model, which we will discuss, and this model somehow is analyzed analytically. I should be fair with you that I didn't fully understand how this analytical consideration work, but I definitely understand it to some good extent, and I can explain some parts of this analytical consideration. And the main value of the article is the numerical calculation of something that I will show you right after I finish this overview of the plan. And then they have some experimental realization that proves both of analytical consideration and numerical methods. And they also have some extra comments, which I didn't read yet because it took me even like for now up to 20 hours to go through all these parts. So I'm not sure what's written in discussion, maybe some extra advanced comments about applicability or potential applications. They also have not little supplementary information where they comment many details and provide additional plots, but let's not even look there because nothing is crucial there, at least in my point of view. Okay, so now let's start with the essence of the article, because that's the best thing we can start from. So the essence of the article is the following, as far as I understand, that suppose, I mean, we always deal with transitional metal Dichalcogenides, as is announced in the title. So these are special materials. I'm not sure how they are really differ from other materials. By the way, if you have some questions, you can put them in the chat if someone is here on the stream. But they are famous because they have they have really a lot of properties. And okay, here if I scroll a little bit to previous articles, so the previous stream was also about this type of material, and they have some special properties of resistance, and I was discussing 2 hours of this configuration of electrons and this special resistance. So this configuration of electrons is a special feature of these materials, and this article gives us some insight of this different configurations of electrons. Here we see what it really looks from physical point of view, but let me add some light. So from physical point of view, we use the tunnel microscopy technique, which is, well, I'm not expert in experimental methods, but in a nutshell, it works that we have a tip that goes through the material, like scans actually, and it scans very fast, so that during one scan not so much states of electrons are changed. And that's how these images were created. And here on each image we see the intensity of electrons. So somewhere there are more electrons, somewhere there are less electrons. And there are different materials with different dopings, and existence of dopings is related somehow with the filling factor. That is the most important parameter which distinguishes the distribution of electrons. Okay, from one point of view, the starting point is that we can measure these different states. And you can see that they are very qualitatively different. For example, okay, they have also labels for all of them. This is domain states. These are, I don't even know, like lattice states or symmetric state. This is the liquid state. They also call it quantum liquid. And they also have some glass state somewhere. But right now it's not really important what these labels mean. What's important is that, yeah, like, okay, maybe the only thing is that there could be domains, there could be chaotic amorphous state, or there could be fully ordered state. So in order to predict which state will be for a particular material, they have some theory, which we will discuss during this stream. And I wanted to show you the main plot from their numerical calculations and theoretical analysis. So this plot is used to describe these experimental observations, which were taken from different articles, by the way. And so let's spend some time to understand the main result of this article. So they say that the main parameter that is used for a description of the states of electrons is the filling factor. What is the filling factor? We will see shortly in the section of the model or in the section of analytical consideration. But like in general, the filling factor is how many electrons are there per unit cell. So as far as I understand, they inject new electrons, and if there are more electrons per unit cell, then there is a different state. For example, yeah, there could be different states, and here we have a sketch of all the possibilities with all the labels that were announced recently. So how this plot works: on the y-axis we have temperature, on the x-axis we have the inverted number of a filling factor, which is denoted by F. So here we have 1 over F. On this axis I propose not to look because that's not that important right now. So that's the phase diagram. So if you pick up any point somewhere there, you can say what is the state. And by state, we mean just how the electrons are distributed. We are not connected it to the current properties. Nothing is discussed about it. We just have the distribution of electrons. Why is it useful? We can discuss later. Maybe it's not really clear why is it useful, but it's interesting, and from theoretical point of view, it's not trivial how to predict the states. Okay. So that's how this diagram works. That look like if you decrease temperature very much, then at low temperature, for as far as I understand, all layered transitional metal dichalcogenides, at least I don't know any material, or I don't remember any. Yeah, by the way, it's a good idea to write this question for myself. Yeah, okay, I wrote this question that I'm not sure if it's valid for all traditional metal Dichalcogenides or only for some particular ones, because here, yeah, we have a lot of examples of them. But what if we change this material to another one, and what is the special feature that makes this theory applicable for them? Yeah, okay, I will add these questions to the section of questions, and little reminder that why FST is the best app for science, because we can easily add these questions here. Right now I mean, of course it's not developed, this is some little problems, but it doesn't matter. Right now I'm not going to create it. Actually, these buttons immediately can create some new sections, but I'm showing you the copy of the project because it's better to open only a copy of the project in the like testing of this app. So I will add this to the real project, which is not opened right now. It's just the copy of the project. Yeah, another good question appeared, and let's assume that this theory is applicable for all TMDCs. So what does this diagram tell us? That if we take any material, we can calculate how many free electrons are there, and this will give us some position of the horizontal axis on the phase diagram. Then we also can measure a temperature which this material has. Another good question which appeared only right now in my head is that we can't plug directly temperature into this plot because we have division over V0, and I don't remember on the top of my head what is this V0. So is it a little temperature in kelvins or big temperature in kelvins? It's also a good question which I will think later. But somehow, if we manage to plug the temperature and the number of electrons, we can have or the glass state, where nothing is ordered. We can have, basically we can have two states except some exceptions. So the first state is the glass state, the second state is the liquid state. What is the difference between glass and liquid? I actually don't understand. Okay, it's also a good question. Yeah, also I had another interesting idea that, you know, like Richard Feynman was saying that to learn something you need to explain this to another person. So this FST application is the best realization of this idea, because you can easily just open your article and explain this idea and get a lot of practice absolutely for free. Also, we can promote the app. That's another idea of the stream. But the main advantage right now is that I just have a great practice in science, and that motivates me to just do it and not even look at number of viewers. So that's the phase diagram. We have two very common states. Both of them are not ordered. Maybe liquid state has more space between the atoms, and by atoms I mean like these electrons that are there that are conducting, because all these images are images of electrons. There are a lot of electrons, so each bubble is an electron if there is a bubble. If there is no bubble, then no electron is not localized much, which also can happen, of course. So there are two states, but there are exceptions, and these exceptions are the very, very symmetric state and state with domain wall. So they are together. So if you have exactly filling of number of particles per unit cell, then you get the crystal state where everything is ordered, and you will see, sorry, need to scroll carefully. So you will see this state in this orange state will be this very symmetric state. If you diverge slightly to left or right in this axis of the filling factor, you'll get a domain state, which is shown here, where somewhere here there is an order, but then there is no order, and maybe there are a lot of things are known about domains. Right now it's not really important. The important thing is that if you have a filling factor somewhere here, then you will have this state, or maybe this also state. And these are the exceptions. These fillings are called filling factors. There are some formulas for them which we'll cover shortly, but I just wanted to point out that this is the main result, that they explain these pictures from microscope by filling factor, and if you just change the filling factor, then you get a different state. Yeah, so we can think about why is it so. That's what they prove in the article. So right now you understand what happens in the article, and if you don't need this information and if you feel bored, you will not miss some really very important and unique statements, because these are the most important and most unique statements. Okay. So let's accomplish our plan, and the first point is in our plan is the introduction to the article and the preface to, yeah, let's just read the abstract and comment the abstract, then I'll go to introduction and give a preface to introduction. So yeah, like you can you inject some new charges using, for example, light pulses or charge injections. That's how you create such different pictures. They write in the whole beginning that it can be used for memory devices, but maybe it's not used for memory devices, maybe it's used. For me, it's very not clear, and nothing is related here to the memory devices. So, yeah, but I will comment very soon one thing that I wanted to comment just right now. It's better to finish at least the abstract. Here they say basically what I said, that they are dealing with this problem. They use the so-called charge lattice gas model that we will see later. These are the magic fillings that I announced. And if we don't have them, if we have a different filling, then we have a different state. Yeah, they claim that there is a new viewpoint, new generalized viewpoint. So I'm not expert in this field, so I can't tell you how new this point is, but I don't understand what is really new, because they cite article which was using a similar approach, so everything here was already developed maybe, but I need right now to close the window because there is rain. Okay, so let's continue this beautiful scientific stream. But I need to click here, and right now we will see the screen. So quantum fluctuations between degenerate states predict the quantum charged liquid at low temperatures. So I should also write myself that. So it's not clear what do they mean by quantum fluctuations, and they don't use this theory, any theory of quantum fluctuations. Why? So yeah, nothing is clear here, and right now I can make this comment, which I wanted to do even before reading the introduction, that at least in my point of view, this article has a lot of unclear statements. All the introduction is full of unclear statements. So it's very hard to read this article. They also have typos, and like, oh, that's the wrong page. I wanted to show you, this is the published article, but on archive they put a draft, and draft has some typos, has some extra statements which are not present in the main article, so don't believe that draft version, better read this version. But I didn't know, so I was already immersed into the draft version, and I don't think that it's really useful. It wasn't. I would better read this version than the draft version, but okay, that's only the draft version with my comments, which has approximately the same theory, but it's the text is way rougher than the final version. So that's why it took for me so much time to prepare for the stream, because the statements are very unclear, and I can just only guess what do they mean by what they mean. Maybe I will do the second version of the stream where I will be more prepared and tell more useful things about the physics in this article. So let's go through the introduction. So here they say that all these things were recently measured. Have they been recently measured? Maybe yes. I didn't check these articles because my button download all articles which should be here is still not working. Here they say that there are a lot of phenomena in this transition metal Dichalcogenides. Okay, so nothing is really important there, which I missed. So here on the first plot, which first figure, which they present, there is an illustration of the phases of TMDCs. Actually, maybe of the titanium disulfide. Why did they choose the titanium disulfide? Yeah, it's also a good question, which I wrote right now to myself. Why the titanium disulfide is better, but they chose this material, and here they show different phases. They didn't comment it, so that's only my intuition how one can understand them. So here you have the titanium atoms. So these are layered materials. So these are two layers, and the phase, which is 1T or 2H, is telling us the alignment of these layers. So here you have the triangular lattice of the same configuration of one layer to another layer, and here we have a tilt of the triangular. I didn't check this information, that's the only thing that I saw myself when I was comparing these images. Why is it called 1H and H, 1T and H, I mean? That's not clear, but I know that it's not clear, so I wrote this question already before. So here, that's the illustration of the material itself. Here we have a temperature and doping diagram. Yeah, actually, I understood right now that so this diagram from my previous stream is not the same as this diagram. Yeah, okay. Should I write myself here? Should I? So one of the questions that was not clear from the previous article, this one, from what state to superconductivity in titanium disulfide by Sipos et al. So it wasn't clear if pressure gives the same behavior comparing to increase of doping, and here we can see some hint, which is not, which we should check definitely. It's not really proven, nothing is commented here about it. But we can see that if we increase doping, then this is how the phase diagram look. And if we increase pressure, this is how phase diagram look. So they look relatively similar, but superconductivity stays constant. Here, superconductivity diminishes to 0, according to all of the well-known authors which wrote this article. And commensurate density wave also goes to the top, and here it stops way before the non-commensurate density wave. So they even used similar colors. They also put, for some reason, the question mark. Here they comment that this region is not really understood. I don't know what is known, not known there, but I understood right now. Well, I will telling you this, that this diagram, so or they are wrong, or it's too schematic, or that's the difference between pressure dependence and doping dependence. In the previous article, they didn't explain this much. They said that or we increase pressure or we increase doping, like it's the same, but like intuition tells that it shouldn't be really very much the same. And like there is a lot of theory about the disordered systems where we have doping, but I don't know anything there about the pressure. So right now we can just guess what they mean. Let me think a little bit about it. What do I mean? Yeah, we can just guess. I mean, like if this model is applicable for doping or not, or model of doping is applicable for the pressure dependence, because like we need to understand what is developed here, what is developed there. I'm sure that there are some works about it, but right now we are focused on this work. Okay, that's what I told. That's my comment here, which I didn't understand much before, because I didn't spot that here we have pressure and here we have doping, and that's the STM measurement that I told you right now recently. Okay, let's look at the next paragraph of the introduction. And as I announced, that's a complicated part which has a lot of statements which just broaden our understanding of the field. So yeah, let me emphasize it again and not repeat all the time that nothing is well explained here. That's always the case of introductions. Maybe after many other articles I will tell you a lot of good comments about what happens here. But right now I can't comment much, I just know what is written there. So they claim that there are three wait a second. Yeah, I need to prepare one little thing. Yeah, they suggest, maybe it's better to say, I have a list of words which are better than the word claim. So they state that there are three mechanisms for formation. Yeah, one is the Fermi surface nesting, another is electron phonon coupling, and some exciton condensation. Nothing is written about exciton condensation, so we can even forget about it. How is it related to charge density wave? It's also not clear. There are of course references, but why do we need to download them? It would take a lot of time, and again, we will just not understand anything. So to be focused, we are just ignoring it. Yes, they claim such an explained, they do such an explained statement, which will be next half an hour at least. So Fermi surface nesting is another statement which is a famous effect where we have a change of a Fermi surface because of some property, maybe because of yeah, what is the Fermi surface nesting? Because of some symmetry of the system. When I'm saying this, I really don't understand why some symmetry can lead to the change of Fermi surface, but that's really well known effect which I tried to understand some time ago. Right now I don't remember. And electron phonon coupling is, of course, it's like obvious what is meant by this, but it's with typical people often say that there are or polarons or charge density wave, and if you have a polarons, then it means that you have electron phonon interaction, because polarization is encoded then in phonons, and electron creates polarization around it. So here they write that charge density wave states are related to electron phonon interaction. Yes, of course they are related, but like it's not very much clear, is it directly related or not directly, because by default I thought that electron phonon coupling is like one framework, another framework is the charge density wave, and right now I don't know any good theory that connects electron phonon coupling and charge density wave. So electron phonon coupling is that famous polaronic theory. Okay, yeah, to be more precise, not always electron phonon coupling gives us the polaronic theory. If you do some very sophisticated transformations, you can get even superconductivity from it, or at least there are some derivations which might be wrong. Maybe that's not the proper derivation, but there are such derivations of superconductivity. And here, by the way, there was a discussion that like in one region of phase space we have superconductivity, and in another region we have the charge density wave. Okay, they claim that they coincide in some region which is not clear where it is, somewhere here of course, but where exactly it's not clear. So when they say that charge density wave is related to Fermi surface nesting and electron coupling, that's actually abstract statement which has no really important value, because we're not going to deal with Fermi surface nesting in this article, neither with select and phone interaction. We will just use the model that I didn't write into the list of main formulas. It's not this one, that was from another article which will be in the later talk. But we have the great application focus structure tool, which we will use to access the required information without any scrolling. And look, guys, it works. I don't even need to do anything. And I mean, there could be a bug, but right now I'm happy that there is no bug. I immediately open the required section and I see the formula that I wanted to show you. That's the formula which we are going to use. Why do we need to know about some Fermi surface nesting and electron phonon coupling? It's not clear, and it will be not clear, and you can just forget all the statements. I'm just commenting it to make everything really clear if we really need it or not. Okay, let's go to the next sentence out of, I don't know, 50 or 60 or 70. I wasn't even counting them. Again, we see a statement which is not very clear, unfortunately. So they say that diverse systems are very similar, but proposed mechanisms are very different. So yes, there are different proposed mechanisms, and it's not clear to which model which mechanism is applicable. I mean, from theoretical point of view, from experimental point of view, we can say, yeah, let's apply this model, get some results, but right now I don't know the criteria of applicability, which is the one of the main questions which I have already posted here in my section of questions. Guys, I'm sorry for this. Okay, we can try to save it like this. Okay. If you will know how to program, please write me, we can collaborate, and it will be beneficial for both of us. No, it's not written here, unfortunately, in the list of questions, but that was the question in my mind for a long time, so I will add it later. And it's written in my mind, that in my head, that the proposed mechanisms are always different. There are a lot of mechanisms for each phenomenon, and what they say that low temperature commensurate states are very similar. It's already, I mean, this plot will be further in the article, so I guess that's what they introducing us to, that this is the different low temperature commensurate density wave state. Yeah, I wrote myself a question that actually, like here they say that's like commensurate charge density wave, but what about this non-commensurate charge density wave? Because here that's like domain state, so we assume that it's a non-commensurate charge density wave. This is only the commensurate charge density wave, maybe here, here, and here, nothing more. So yes, they are very similar. Yeah. Okay, so here they write only about this state, or yeah, maybe it's a good plot which I should also add to the main plots, because here we have doping, before we had pressure. So if we speak about this area of this phase diagram, then for different materials, this phase is similar. That's why we call them the same phase. That's the question that I wrote here. That of course, if the phase is similar, then the state inside of the phase is also similar, right? Because that's how we define what is the phase, where it has some similar properties. So that's also like useless actually sentence where we see like obvious claim that like all phases are similar. Yeah, like, or at least it's not clear what is the state, because by state I thought it's a phase, and if it's a phase, yeah, same phase in different material looks similar, obviously. And obviously there are different mechanisms for explanations of them. Then they say that this mechanism of Fermi surface nesting is questioned because one author, okay, by several authors, it's not clear why is it questioned. Yeah, also I wrote here a comment that actually there is a Fermi surface nesting and electron phonon coupling, and they jump, the authors of this paper jump from Fermi surface nesting to electron phonon coupling because maybe they assume that this is the same mechanism. I don't know why do they jump from one mechanism to another, or they just like to do different claims about unrelated topic, or they assume that Fermi surface nesting is very much connected to electron phonon interaction. And I mean, yes, of course, like there is a lattice, there are electrons, because of interaction there is a nesting, but electron phonon coupling will mean a specific theory. Like there are several models that are well known, like Fröhlich-Hamiltonian, for example. Yeah, I wasn't doing a stream about it, but I thought to do it. Maybe I will do later. So for me, it's not really clear to which exactly model the Fermi surface nesting is connected. And for some reason, they say that, like, what? It's related, but it's questioned. So is it really important to know something about Fermi surface and nesting or not? It's not clear. They say that this mechanism fails for this material. But for this material, iridium, titanium, T3, T3, for this material, this works method. For these two materials, this method doesn't work. Yeah, okay, based on this part of the sentence, we can guess that they mean that there is another electron phonon interaction and electron phonon coupling. And sometimes this works, sometimes Fermi surface nesting works. It's like, because like they write, this mechanism is questioned, then there is another mechanism which works, but then it also fails. Why do they have the word also? There shouldn't be a word also, because there wasn't a fail before of Fermi surface nesting. They just introduced it, and that's all. And there was nothing. There are some questions. Yeah, of course, there are a lot of questions everywhere in condensed matter. So this word also is the wrong one. Okay. Butcher density wave approach. Well, that's what I knew before, that Fermi surface nesting is very much connected to charge density wave. But that they say that there is some electron phonon coupling model which is also connected to charge density wave. And here the electron phonon coupling explains something that Fermi surface nesting doesn't explain. Okay. Luckily, there is this end of the paragraph, and we are coming to the second paragraph, which was deleted from the final version, which I didn't know when I was reading it. So I will not comment much here because nothing is very clear here. They say that there is some strange model which you will not see anywhere because no one is working with this model, and this article which is cited here, it's not even available. It's available if you do some special logins to some special accounts. So in a nutshell, no, it's not available. No one is interested in this model for a very, very long time. And also they say that for some reason this model is not working. So why did they decide to choose the model that's not working to describe here? It's for me very not clear. Yeah, and they claim that this model gives some gap. So I don't know anything about it, and this model is already forgotten, so all the statements can be just thrown out. That's what exactly they did from their final version of the article. Now there is a statement about some anomalous peak of resistivity. What is this peak? I have no idea, and the only way to understand it is to read this article. But maybe it's a rather well-known property of titanium disulfide, and they also say that it's not connected with the model that they only mention here and never again. Okay. Yeah, basically that's everything what's written here. So they say here in the next sentence that there are some phenomena which are not explained by wait a second. Yeah, like I see the statements and they feel that the stream will be a very long one. It's already 50 minutes, but we haven't covered much. But that's how this article is written. Like, we need to deal with the information that we're given and not hope that it will be an easy thing. So they say that there is some special charge density wave sliding, and there are some special topological defects which will be commented later. What is a topological defect here, I don't know, and what is in general topological defect, it's a big topic which I'm not an expert in. So how is it related to a real topology? It's even a harder question, so it's better even not to ask this question. But these defects somehow govern transport, and there is some behavior and high fields. So they need, because of this, they need to readdress some nature of the state itself. So what is meant here? Well, but basically nothing. It's not related really to this thing, and the main point of the article is to explain this observation using this basically model, which can be somehow analyzed analytically and computed numerically. That's what it happens. So here you can also forget the statement, this sentence. They say that, oh, there are some effects, yeah, which are not related to the observed effects. But that motivates us to think more about this material and propose a model which will at least predict the state. And maybe the state is related to behavior at high fields. Maybe it's related to topological defects or sliding. But if you want to study how it is related, you can write your own, I guess, article, because here this article will not help us to understand it. Okay, now they return to the Coulomb interaction. Okay, not return, but they mentioned first time the Coulomb interaction. So that's a good statement, which I was thinking in the previous stream about, that here in this article by Sipos, they were thinking about Coulomb energy and calculating it somehow. So this article says that the idea of Coulomb interaction comes from these two authors, Tossati and Fazekas. And other papers confirm, I guess, that this work of Coulomb interaction gives us the large gap, because that's an insulator. This is this behavior. And onset on metallicity, that's what I don't know. Yeah, so it's not clear what does it give us, but some special Coulomb interaction which can be added to the model can give us explanation of what's going on here, which was actually maybe even done in this article with maybe similar method, because they were struggling with some Coulomb interaction. And some special what is it? Where is it? Onset metallicity. What is onset metallicity? We don't know, but there are like 5 articles, so you can spend whole day figuring out what is this onset of metallicity. Then what do they say? Okay, there is another one approach, so I don't know how they supposed that we were reading this. So here they say that for charge density wave there are these 3 methods. In scope of them they discuss only 2, that some is questioned, another is confirmed. Then they say that there is the model that fails because of some effects. Then they say that, but there is another one, Coulomb interaction. Now there is another one, band structure calculations. Is it related to Coulomb interactions? I guess no. I mean, philosophically yes, but in practice no. I guess there will be just different formulas here and here. And they say that the next one method, band structure calculations, gives us strong, give us some in-plane gap. What is in-plane gap? Of course, it's not clear, but there are some citations as usual. Okay. Yeah, so there are different viewpoints, and now there is the next viewpoint. I mean, the next approach, which is, you can guess how it is related, but only guessing can be done here. So degree of correlations, whatever it means, should determine in which state we are. There is this also in CC. There's also this new state which I didn't mention before, in commensurate charge density wave. What is it? It's very known in this community, but I don't know yet. Okay, then the return to one of the previous methods, electron phonon coupling. So here they conclude that there are just different methods. Issue have not been resolved. Well, they don't state any particular issue. They said that like different authors wrote different things, which happened always in science. So it's not clear which exactly open issues are. Of course, there are a lot of them, but which exactly they mean here, it's not clear. Okay, now maybe there will be a more meaningful paragraph. Yeah, now they say, okay, maybe I shouldn't say that more meaningful, because there is meaning in each of them, and this paragraph doesn't look more meaningful than the previous ones. They also look how they write, not easily understood using established shared density wave theory. So there is no way to even try to guess what they mean. Is it understandable or not understandable? Does it work or not? It's like, you know, when you are not sure very much and you can't say I don't know or do know, you can just say like I know it in a way that it's not easily understandable. So let's skip this question. Yeah, there is this scanning tendril microscopic. I mean, when you read this question, we immediately think, why do you need such a lot of text? You can just write the model, give like, I don't know, this size introduction, and give the model. Then, so as you see, it's not a little article. It has, we don't count these references. No one needs to count. It's like 13 minus some, like 11 pages approximately, because minus 1 this page. Okay, it's a 12 article page, so it should be way less in size. There are a lot of very unclear statements. And by the way, that's the article from archive and from publisher, and this is the article from archive. It has 32 pages, and that's okay. But we count also citations. There are some figures, so it has even more pages. But it has also the supplementary information, and this is the supplementary information, which is 18 pages. So totally this article in this layout is 50 pages. So do we really need 50 pages? No, definitely we don't need 50 pages. Thank you for interesting statements, but no, it would be better if they wrote exactly what they need and to say. And what they need to say is that this experiment is explained by this theory. They also don't much dwell on how they exactly get these results from this model. They just say that all Monte Carlo simulation, well, if you're expert in Monte Carlo simulation, you will understand it, but for me, it's rather unclear. So let's continue our journey through the introduction. Yeah, that's the empty statement. Okay, they say that there are domain walls, and domain walls are in other places. I mean, if you do something else with your material, like charge injection, ion substitution, so maybe a lot of people were thinking about these domain walls very intensively. You might ask, why do they need it? Don't ask me. They claim that for memory devices. So if you don't know why you are doing some things that you are doing, you can just say like for fast memory devices, and it will be enough, because that's what exactly they say here, that the only motivation was written in the abstract for some memory devices. Why? We don't know, but you can go always and read the side paper. Okay. Yeah, and there are other reported phenomena. Why do we need it? Just write the authors this question, don't ask me. Let's go to the next paragraph. Yeah, they say ultra-fast memory devices, as I said as written in the abstract. And again, they say that something is not easily explained. So is it explained or not? We don't know. Here, it's not easily understood. Here, it's not easily explained. So nothing is really useful here written. Then they report another effect, some lock-in transition, whatever it means. Okay, we also know that this material has some superconductivity in it, and I mean, which material? All the transitional metal Dichalcogenides, or at least some of them. I don't know. Actually, it's a good question if all or not all have superconductivity. But they say that in these two special materials, there is a superconductivity that can happen. And this superconductivity happens in this domain wall state. However, they clearly draw here the diagram where domain wall state is here and superconductivity is here. There are different states. Maybe we should understand this diagram that superconductivity is inside of domain wall. Maybe that's what they propose us to do here. Yeah, let's see how far did we go. Yeah, and also like it seemingly coincides. What does it mean? Is it happens when there is a texture state, or is it not when there is an appearance of a textured state? But as we saw on the diagram that I showed you recently, the texture state appears there where there is no superconductivity, so it's again a useless statement. I mean, you should like draw a diagram for this material to show us where superconductivity and where there is the main state, and then tell us, look, that's exactly what we mean. Here it's not done, but we have citations, of course, so you can go and look at citations. Okay, now we have again useless sentence, unfortunately. There are some k-space interaction. K maybe is a momentum, but they use only here this terminology k-space interactions, which is maybe a synonym to interactions of electrons. Okay, that sentence just teaches us how you should write sentences if you want to read a long text. So instead of saying that some theories that will be not needed are not sufficient to explain some phenomena that are not really relevant, they write a long, complicated sentence with complicated words. Nothing is important here. You can just forget this sentence. Basically, it's written that previous theory is not applicable for some of materials, which is obvious statement, right? Okay. Just wanted to show you that I didn't delete the text. See, like that's the original text. So they say discommensurations. See, like that's not I deleted something. That's okay. Believe me that if you go to archive, you will get exactly this paper. They don't say anything about discommensurations, but then they claim such discommensurations. So there is no way to understand it. Something of this. Of these features, what the features mean, it's not clear, like some of effects where were discussed. What do we mean by discussed theoretically? Is it meant by the creation of the model or what? And we can see the statement that, I mean, again, comparing to the article from the previous stream, from this article, they also said that there was some works based on Landau functional. Here we also see this, that this famous person for superconductivity tried to describe something which is not clear what, but in this transitional metal Dichalcogenides. What is meant by regular structure, it's not clear. Actually, this article should be just rewritten. These sentences are not informative. They just distract us from the main result and nothing more. Okay, maybe next paragraph will be more useful. Okay, let's read what they write. What they wrote. Okay, they claim that there are strong correlations. They haven't used ever any correlations. They will be just later speaking about long-range order, but you should think, oh yeah, I see that I'm there, so you don't see it. So that's the essence of the article, that this model is used. When you look at this model, do you see, sorry for this scrolling of the PDF, that's just a bug. There shouldn't be extra scrolling here. Where is it? Ah, yeah, here. So they say that this is a viewpoint of strong correlations in spite of this work. Is it connected to this work or not? It's not clear. Is this model a model of a strong correlated electronic systems? Maybe. Oh, sorry. Maybe, but it doesn't look so, right? It's just a tight-binding model. We will go through this model later. But for some reason, this model is called the model of the strong correlations between electrons. Then they say that since it's done in spite of this model, but not only it's done in spite of this model, but also have origins in another model and in another model. And then they say they will use numerics. Here, I don't see any value right now in this sentence, and there is a comment from me in the past that it's better to forget this statement, the sentence. Okay, so what is meant here? That so again, it's a very unclear statement because Chern density wave does not imply. Yeah, I mean it implies, but it's not the theory of polarance. That's a purely different theories. If you take a theory of Chern density wave, book about Chern density wave, you will not derive some results from book of polarance. And if you take a book of polarance, you will not derive results from Chern density wave. At least that's what I tried personally. And here it's the mixture of different words. And for some reason they wanted to say about this high frequency dielectric constants and static dielectric constant, which play important role in the theory of polarance, as I was showing recently on the stream about polarance. But maybe it's better to do another one stream just purely about this Landau-Picard model, where they introduce a parameter that depends on both frequencies. Yeah, but we don't need to know this right now. It doesn't play any role. It's not connected to anything here. And experimental evidence, not like common sense implies that electrons are effectively coupled to lattice. The theory of polarance implies it. Then there are some consequences on the experimental side, but it's not working like experimental. And yeah, there are then confirmations. But it's not working like, oh, we look at the experiment and we create theory to... I mean, sometimes it could be working, but often we just create theory, then try to find something in experiment that confirms the theory. But it's like obvious that they are coupled. It's not like experimental evidence implies that, like common sense is already enough to tell us that they are coupled. And well-known theoretical investigation of polarance has already given us this model of coupling of electrons to the lattice. Okay, let's go further. Okay, then they give us introduction to this model, which will be later that yes, that's a simple model, but there are some reasons why they use it. Okay, then they say okay, for some reason they say that this model has slow motion of electrons, but this is a hopping model. So how to get how to increase the speed? We don't have a, I mean, it's not a hopping model, it's just a model of energy of electrons. We don't have a kinetic term, we have only a potential term, and by slow down we mean, exactly, I guess exactly like this. Then they have again a collection of citations where this charge lattice gas model is used in many things that are very not related, so it's better even not to waste time on this. And some other models also have this charge lattice gas model. Is it exactly the same? I don't know, because I didn't check these citations. Why would I do it? It's a waste of time. Okay, then they say that actually this model was already used to the same material that they study here. And there are some photoinduced states. What is meant by photoinduced states, I don't know. Maybe they have some formulas further below in the discussion, but I didn't get to them. So yeah, let's just believe that maybe here it's meant that the model we have only not excited state, but state with bigger doping. And if it were excited, but it's equilibrium, yeah. And if it's a photoinduced state, then it's a non-equilibrium state, because maybe some light is constantly shining to the material. And for this case, the charge lattice gas model is also applicable. And since other people have used for unrelated materials, and some people use this model for this material, they say that that's why we are going to use this model also for this material. And that's the statement that I told you before, that here we have a different feelings where there are special properties. They call them magic feelings. So yeah, we will see later the arrangements. don't know why did they write it here, because it will be written again further below. Then they are also fascinated about the long-range order, which they don't like explain in terms of formulas. It's just the word, which may be used as a criteria as a difference between liquid and glass state. But for me, it's not clear how to find out if you really have a long-range order or no. What is physically meant? Like, I mean, there is a definition that there are some correlations over long distances. But I don't yet have an intuition about the state, like we see here, one state or another state, where, how can I say that here there is long range order, here there is no long range order? Okay. Okay, basically that's the, again, description of this image, which will be described also below, that well, basically that you have different states, you have at the special numbers some special states, and you have some domain walls if you have feeling close to this special magic feeling. So nothing is very special here. It's introduction to the statements that will be further. Then final introduction will be soon over. So they connected with quantum spill liquid. What is quantum spill liquid? They don't explain. There is this citation 104, so maybe that's enough to explain what is a quantum spin liquid. Actually, here they comment what is a quantum spill liquid. They say that a superposition infinite number of valence band states, but what is really meant here, it's not clear, and how is it connected to the name quantum spin liquid is also not clear. And it's not clear what is also meant here, but they said that the ground state entangles all the states. That's the very strange statement. I can't even imagine it, how one state can entangle other state. Like usually people, like if you have an external experimentalist, he can like move some states or entangle them, but the ground state directly entangles other states is an unusual statement for me, which I can't comment. I don't know what is meant here. And they also from time to time refer to first order phase transition, and they don't clarify from what to what phase transition. But somewhere there is no first order phase transition, maybe from glass to liquid, which is like obvious because they even look very similar. And they also say, not only here but also below, about quantum critical points. It's not explained what do they mean, but somewhere there are no such special points, which might be there. Yeah, which are in other some quantum models. It's not clear what's meant here. Yeah, they say that this is related to this phase diagram that I was already showing you several times. Yeah, and then they finish with the last paragraph, which has some sense, that they state that some people who are interested in glass formations, they believe that to have a glass, they need to have the crystal state, and then glass is because if you calculate energy, system is stuck in this local minimum but not the global minima. So if it had a chance to go from local minima to global minima, then there will be no glass, but there will be crystal. And their calculations, it's not challenging, but they disconfirm this assumption. They say that no, actually the minimal energy will be of the amorphous or glass state, and something should be reconsidered in this theory of glass formation. But in announcement in the abstract they said about memory devices something, so this is divergent from that useful direction to some strange direction that wasn't announced before, that they also want to discuss some glass formation features. Okay, then I also have here in insertion of part from supplementary material, exactly the text that they wrote with my comments, and they say that hey, charged lattice gas is used in some other places with some other names. Here there are some citations for you. It's better not even to read what's written here. First of all, it's useless. Second of all, it's not clear. You would need to open papers which are absolutely not connected to the result here. So it's better to forget all these unnecessary comments. And finally, we have covered the introduction. So summary is that there are different, okay, this is the transition metal Dichalcogenides. There are different models and effects that are present for different materials. Something is not working, but there is a charged lattice gas which is used by other people, and then some abstract statements, and then again it's used by other people, and then introduction to this image that that there will be some fill-in factors, and there will be different phases based on these fill-in factors. And then they connected to quantum spin liquids and glass formation. It's not very clear at all what are the parallels. That they say that similar situation when the polaron charge configurations, because there are some entanglement. So they found from somewhere some entanglement, then they remembered that, oh, in quantum spin liquid there is some entanglement, then maybe it's connected. But also there are some people who are doing glass formation and they assume something that is not assumed here, and they say that, oh, it's actually that some ideas there, it's not really true. It's not really a big statement, but maybe someone in glass community will be interested in this statement. And also charged liquid gas is used somewhere there. So that's the summary of the introduction, and now we're coming finally to the model. And to remind you what is left, so we covered this thing, have this, but also this. Maybe we'll go a little bit faster because it's too slow, but it's better to do slow but with a high quality. So now we see the main model, and that's very important part of the whole discussion of this article, because everything comes from this model. All this plot, all this predictions are made from this model. It's interesting to check how really this model is strong for predictions, and as far as I remember, it does indeed predict all of this. So looks like a powerful model. Unfortunately, it's not written here where is it taken, because it's taken only from common sense. So that's so we have just sum over all sides, and okay, let's check the original, the published version. So okay, so maybe it's meant that electron, I mean, n is the density of electron, can be or 1 or 0, but you can also look at it in terms of creation annihilation operators, which is not written here. They assume that people know this because they assume that they worked a lot with the dividing model. So n is the occupation number of electrons on different sides. I and j run over all sides, but if we have a two-dimensional plane, it's not clear what is meant by I is less than j, because it's not a line, it's a plane. We need to have some order, and it's not clear what is meant here by I lower than j, but I assume that the sense is that it's just different sides which are not the same, different ends. So electron, which is called here polaron, can hop from one side to another, and this is the constant which is there to tell us the energy of the system. Because this electron, I mean, no, okay, it's not the correct, it wasn't the correct explanation. Electron can't hop, it can just stay there, and this constant tells us how much energy does it have because of interaction with another electron. And this sum is telling us that we are going through different pairs of electrons. It's not the correct way how one should write it, but this is the idea. This constant is different for different electrons with different distance between them. So it has this constant in the Hamiltonian has two different constants, V0 and Rs. Rs is just a screening radius, which is taken as a constant, like value, I don't remember, it was 3, as far as I remember, maybe 3.5, but there is a investigation of this, of dependence of the energy on this constant Rs. And V0 is always a constant. I'm just interested, I was interested here when I was speaking about the temperature, how much should we have temperature to have these phases, and to get this value of temperature we need to think a little bit and calculate this value in proper system of units. We know the charge, we know, okay, we don't know, but maybe even ChatGPT can tell us the value of lattice constant of titanium disulfide, the titanium disulfide. Calculate. I wrote myself in my to-do list to calculate later this constant. And that's how we can find out where exactly we can have this phase transition. Okay, then there is this R I and J, and R I and J is the distance between the sides where there are some polarons. By polarons we don't mean anything else, we can also call them just electrons, because absolutely nothing is used here from theory of polarons. Yeah, and we also assume that there is this atomic lattice and there is a polaronic lattice on top of the atomic lattice. And later in analytical calculations, there will be some explanations of the properties of polaronic lattice for it to have this special crystal state. So everything is in scope of lattices, like atoms, atomic lattices, and then polarons, and they are on top of one another. That's how it's proposed to describe the titanium disulfide and distribution of electrons. Yeah, and they say also that they introduce temperature dependence. And then they say not the correct statement. No, this idea is not coming from this chapter. They have told us already in introduction where does it come from, and don't even try to reproduce it from this chapter. It will not work. It's a wrong statement. I know it because I tried myself a long time ago. Let's forget this statement. I will rewrite it to make it very obvious that it's a wrong statement. And also they neglect spin effects. They have some T-tiled. What is? Yeah, the T-tiled. They don't have the hopping term. They could just write that there is no hopping term without this T-tiled. I will just comment it that it's obvious that nothing is clear here, but it's meant that there is no hopping term. And for future discussion, there will be supplementary information, which is right below in analytical considerations. So congratulations, we have covered the second out of 5 chapters, the model, which is the most little chapter out of all. I just think that there is some rain that falls on my head. But okay, it doesn't matter, it's not a big rain. Okay, so we are coming to the next chapter, the analytical considerations. And there is a big idea. Not so complicated one, but also not an easy idea. And I don't yet fully understand this idea, but I understand it to a big extent, so I can explain you something. So if we take this model, the goal is to reproduce some behavior. They also claim that they compare the numerical idea and analytical idea, and they report some comparison. I'm not sure how to get some results from this analytical consideration, except this like filling factors, but it's also we see that there is a temperature dependence on them, so it's not clear why if we have the same temperature here, if we just increase filling factor, we will still not have an crystalline phase. And crystalline phase starts only on lower temperatures. This dependence is not explained in the article. Okay. Maybe right now I will switch to not to the comment in text from the comment in text to the explanation from myself. Because for example, of the time reason, because it's already nearly 2 hours of discussion. So as I said before, there are 2 lattices, polaronic lattices and atomic lattices. Atomic lattice is just fixed, and polaronic lattice is the lattice of electrons that can be in different configurations. And there are 2 parameters, the r and theta. R is the distance, theta is the angle on this lattice. Below there will be images from supplementary information, which are really essential, so I don't know why didn't they put it in the main article. But okay, here they have already written in the main article. Then they define a hexagonal symmetry where we can do rotations. But okay, maybe it's better to explain from something below what's here. Here I also wrote here that I need images, which I didn't write yet. Okay, so look, let's go to the supplementary information and start with this image, because that's the best way how I can explain what's going on here. and all the text before, just a confusing text, which is also not enough to explain what's going on. So look, there are some atomic sites which correspond to the atoms, titanium atoms, I guess, or another version is titanium disulfide molecule, and the whole material is the collection of these titanium disulfide materials. So it's not, I'm not sure what exactly it corresponds to, but it definitely corresponds to atoms because they call it atomic lattice. And on top of it we have some polarons, and polarons here are colored as gray balls. So if we have a perfect filling, so perfectly polarons coincide with the sides of atoms, then we will have this crystalline phase. And the question is that what is this filling that gives us perfect coincidence of the polarons and the atomic sides? Another question that immediately comes into my head is that we claimed that we have this model. Let's look again. Where is that PDF? That's this model. This is the model that we have, and how this analytical consideration is related at all to this model. That's a good question, which I will ask the author of this article in some days. And will this analytical consideration be valid for some other models, some other materials? I don't know. Well, the main idea is that the state which is realized here comes from the minimalization of energy. So to have the state, we need to have a minimal energy. And if we have this perfect filling, then there are more terms here in the Hamiltonian, because actually, yeah, I don't know how to explain it, because here we have Rij, and Rij is I minus Rj, but if they coincide, then we get infinity. So something is wrong, but maybe we can save it by saying that electrons are on top of the layer, so there is still some distance between electron, site of electron, and the atomic site, and that's how this model should be understood, that we don't have a two-dimensional actual material, but we have a like layer of conducting electrons on top of the just flat two-dimensional material. However, we also remember from even this article, yeah, here they explicitly draw titanium disulfide model, which is not a two-dimensional material, but there is a partial also dependence of this structure. I mean, onto the third direction. And so I need to ask the author of this paper, what does he mean by this model at all? Where is this? By this model at all, right? You have a plane, but we don't actually have a plane. Then if we have this coincidence of polaronic lattice and atomic lattice, okay, maybe that wasn't the correct explanation. Maybe here actually we have only interaction between polarons themselves, and we fully neglect interaction of polarons and atoms. And if we have such distribution, then they are more densely packed. So okay, let's stick to the second version of the explanation, is that we don't have any interaction with atomic sites, but we have the interactions in between electrons themselves, and this interaction gives us some energy. And if we have such distribution, then the energy can be the lowest. But then just it's not clear why, if we had not such nice enumeration of polarons, then why wouldn't we have that distribution? Sounds like also can be. So that's not a clear statement, but the claim is that somehow if we have this distribution of polarons, then we will have this special feeling where there is the crystal structure, and on other feelings there are no structures. And let's look at least how to find out what is the feeling that corresponds to the particular structure. So first of all, we need to figure out how this distribution of polarons is related to the atomic lattice, because the feeling is defined, as I will show you soon, by this formula, which is taken from the main text, and right now that's the image from appendix. And so let's just believe this formula, which the author of the paper, I mean all authors of the paper wrote for the filling factor. So here we have the primitive cells of the polaronic cells, and all the primitive cells can be different ones. So here there are two vectors, and this is the law of cosine for 120 degree in between vectors, and this degree is fixed, as you can see, for the primitive cells. That's always fixed because that's the degree of the atomic lattice, because it's a purely triangular atomic lattice. And that's why if we want to calculate the third line of the triangle, we use the law of cosine, and that's unclear because it's not explained in the text, but somehow this third line is connected to the filling factor. Okay, let's see how we can reproduce some filling factors, like here, for example, if we have this image. Suppose we have polaronic lattice of this size, then x and y are 1 and 1, because this is the value of the one. Yeah, of course, everything is calculated in the unit of the atomic side. So this is 1, this is 1, this is the length of side of a triangle. So that's 1, that's 1. So if we plug to this formula, it's 1 plus 1 plus 1 equals to 1 divided by f, so it's 1 divided by 3. Let's look at this thing. So a is 2, b is 1, so we plug 2 squared, it's 4, plus 1 plus 2. So totally it's 7, and here it's 1 over f, it's 1 over 7. And on this thing, I didn't succeed much, actually, unfortunately, when I was practicing, because if we... so how does it happen? Like, look, here we have two sides, and here we have two sides, so it should be like 4 plus 4 plus 4. That's what should be, but in this case it would be this thing, 2 plus 2. So for it to be true, we should have the second vector as 0. Only then we will have 1 divided by 4. For me, it's a little bit not clear, yes, because formulas work, but why do we have b equal to 0? Why wouldn't it be just 2? Like, Okay, this may be a detail which is not clear, but later if you want, I can do the stream again and prepare myself more. But if you spend at least 15 hours on just this article, maybe you will come to exactly this level of understanding that this formula works, but for some cases, for this one, and this one, I don't know why do we need to put 0 as the y coordinate if we actually have this non-zero value. But okay, that's the general idea, which is explained here, that we have the parameterization, then this is the fixed degree, there is this hexagonal symmetry where we can basically, yeah, I should put this very useful picture at the top of this section, that if we like reflect with the symmetry this or any of other like rectangular, then you can feel this, how is it called? You can tile all this plane by these rectangulars. Yeah, that's what they write somewhere here. And that's called the hexagonal symmetry. That's why we are at all considering just one dead cell. Then we introduce this system of two coordinates of angle and the distance. Then there is this sentence which I tried to understand, but I didn't understand. The statement that we can find the filling factor as this formula, which is law of cosine as it's stated, of course, but no, it's not clear why the filling factor is the length of the triangle. Maybe oh, well, of course, there is some idea that here, for example, like if we go like this, then look like we start from this line and we finish on this line, so they're separated by three segments, and one atomic site is one segment. Like that's one thing. If multiplied by 3, we get the whole this shape. And here we have the atomic site like this, so we need to go how 1, 2. Okay, right now I don't understand why we have such a filling like this length. Yeah, we can calculate the length, but why is it connected to the filling factor? Here this idea works because we have these 3 segments for the for this object and 1 segment for the lattice. But here it doesn't work because we have not integer number of the segments. If you go along this line, it's not the 4 value of atomic sites. So that's the question, but I'm not able to answer it. It's not explained here. So I'm leaving you just with the statement that that's the filling factor that is determined by the distances. That's the main formula, but there is another formula from appendix which also takes into account that's another definition of the filling factor, and it takes into account the particles in the unit cell. So I will comment it a little bit later. Right now I don't understand why we have this number of particles per unit cell. Okay, it's obvious. I mean, it makes sense that we need to multiply something by this number, but this something has this this formula, which I can't also explain. Some multiplications of the constants. Some constants come from the, what is n0 by the way? So some constants come from the atomic lattice, like K0 and L0, and some of them come, yeah, no, both of them come from the fundamental lattice. Okay, we'll finish this chapter, then we'll have a little break, and then we will continue to numerical examination of what happens here. Because they got some results. Oh yeah, there are actually some other beautiful pictures from numerical calculations, so we'll come to them later. But the idea of this analytical considerations part is that energy can be maximized if they coincide with atomic lattice. Polaric lattice coincides. There are not so much different ways how they can coincide, and if they coincide, then for some reason they are packed more tightly. That's how I understand. And if they packed more tightly, then this energy is, or maybe vice versa, maybe they are less tight packed. That's why this energy is the lowest, and that's why it's more preferable to stay in this configuration. Yeah, because indeed, if they are tight and more, then the energy will be higher, and we need the lower energy to have the ground state of this type. Let's check that I didn't forget something important here. They say that there could be also a domain wall in some other case. And in not magic feelings, the system is frustrated, as was announced before. Oh yeah, then they make important statements which they don't develop much, but they say that these analytical schemes were proposed by this author, so it's really essential to read these papers which are cited here to understand what do they really mean, because yeah, they can parameterize, yeah, okay, it's not really explained here, but there could be a great reason why exactly this formula for the filling factor works. And okay, but what to do next? And the only thing that's written in the article, what to do next, is to follow work by these two authors. Yeah. Okay, and that's basically all. Yeah, and they also have some discussion about, I mean, some statements about number of polarons per unit cell. And I don't really know how it coincides with this thing. I always assume that there is one polaron, but there is this strange kappa, which I will comment very soon. This one, which takes into account how many particles there are per unit cell. And so for me, it's still a mystery how this enters the game and how it is connected to the statement that we have this alignment of polarons. Okay, let's look finally, before a little break, to the supplementary information, where there are some ideas about the same thing that I told you. We have just extra formulas for extra particles per unit cell. So if you want to understand, I think the only way to do it is to read these two papers. Okay, first of all, we do this parameterization. We have two lattice vectors, which are just constant. Okay, they're also drawn here. A and B, they are drawn, but for some reason we have the star, because maybe star corresponds to polaronic vectors. I'm not a little bit sure. Yeah, like I didn't read it to such a big detail because they say like atomic lattice primitive vectors and then they draw star. I guess star doesn't mean anything at all because here we have A0 and B0, so I assume that this is exactly A star and B star. And if we have extra particles, then they have also the same, okay, the coordinate of them can be written in this similar way, where we have integer times the vector. Then there is this strange formula for the filling. It uses only these integers. We multiply this one by this one by this one. Yeah, maybe it's a good idea to ask ChatGPT to derive this formula, but I haven't done it. I just don't understand this formula, but the claim is that this is the formula and it's consistent with this thing. But I don't understand it. I will not pretend that I do. Then we have the formula for the energy. And maybe here it's meant that I is not equal to J because of this reason that all, it should be not less than J, but I not equal to J. And of course it means that for all different I and J's. I think that's the typo. And here we see another version of this formula. So for all polarons that are there, we have this n's equal to 1. So we just have the sum over energy, because we assume that that's what do we assume? Yeah, because we'll assume that all states over this lattice over which we sum are just occupied. What if we don't have some particles? It's not clear, but there will be most likely some non-equilibrium dynamics, and here we're interested only in equilibrium dynamics. So that's why there is this formula for the energy, and there is some origin of 1/2, which I was thinking before. Right now I wasn't thinking about it. But the idea is that if we sum over the k and l, which are different, then we will have for 1k all the l's possible, then for all the l's 1k is possible, so there will be two terms of the same type, so that's why we divide by half. It just is related to the fact how we understand the sum. And then there are formulas for the more particles per unit cell. For example, if we have 2 particles, then this R is entered here and we need to sum again. But now for this R, so this R, which is fixed, it interacts with all other particles which are in the, as far as I understand, in the perfect alignment in the polaronic lattice. So this lattice is fixed. That's how I understand it. So we just insert somewhere here any place where we want a particle, and it just will interact, and all the others will stay as they are. They will not move, because that's what this formula is telling us about, that this is the coordinate of other objects. So A and B, they are telling us the primitive vector of polaronic lattice, and they call it particle lattice, which is meant polaronic lattice because particles are the polarons. So these are the primitive vectors of the atomic lattice, A0 and B0. A and B is the vector of the so this is the A, for example, A equals to 3, A0. And B equals to, I don't know why they called B equals to 0 for that case, but okay. Okay, then this extra particle just interacts with others, which is strange because like intuitively others should just rearrange themselves and you will have a different sum over different configuration of a lattice. So that's a good question. Why do we have the same sum? Okay, we don't have them equal to 0, which doesn't matter much actually. And for 3 of them, we have the first one, the second one, and why there is the third term. And there is also a typo that should be, of course, L here, but maybe it's like no, I don't know really. Okay, maybe it's meant like interaction between both of them. But why then we have this term here? It's not clear. I didn't write this question here because that's the advantage of the stream where you can clearly see if there is any mistake. Then they somehow entered this configuration of the site to the computer and said that we will have a finite system of this K and this L, and K and L are the integers, so that's how I understand it, that we are having the finite system and summing over this finite system. They also claim that if you do this for the finite system, then it's not a big problem, because if you even were calculating something more, then this error will be very little. Right now I actually don't understand, but when I was reading this I thought I understand, but right now I don't understand that. Like what is meant here? Like why do we integrate? Like I mean, it's not a trivial place. Like we sum over all the particles on the plane. So if we fix the number of particles, then what happened? Yeah, like that's what happens here, that over y-axis and over x-axis and the tilted y-axis we have the finite number of particles. But why this I mean, because if we had infinite systems, then of course the energy of the system would be way bigger than the energy of a finite system. Why do we have this correction of this form? That's what I don't know, and that's what I overlooked when I was preparing for the stream. I thought it's like, yeah, just an error, and indeed it's just an error, but how exactly to understand it? That like what are we doing? If we fix the system size, then we will not have this term at all. Let me a little bit think about it. Maybe we fix one cell and find the energy of interaction of this cell with all other cells. But it's written energy of the system per one particle. So it's not clear, like not clear at all what is meant. KAB. So here in the formula of the V, we have interactions in between particles. So we sum over all systems. Why do we say that per one particle? And they say also simple lattice where kappa equal to 1, but then they say that kappa is about the number of particles for the unit cell, so it's not the simple lattice, it's not about lattice, it's about number of particles. And per one particle, here it's written, here it's not written, the energy is defined, it's meant per one particle. So it's not a good explanation. There is no way to think more about it. No reason. This is the claim that somehow whatever it meant here, the energy is calculated by this formula. What is really meant by energy, it's not clear. Why there is this error, the error is little, it's not clear. It seems definitely from the definition of the energy, what do we calculate? And most likely the definition is that it meant that just one cell interacts with all other surroundings. And of course, then, yeah, look, for cells that are far away, their energy is less and less because we have here the exponent. But it's not written here, and we can just only guess based on the common sense. And okay, the last part of the analytical consideration is that the picture that I have already described before, because the basic explanation of what's going on starts with this picture. Yeah, it's like a parallelogram, the good word. Let's read what they write here. So this coloring will be later used for the description of distances. I will return to this picture to comment how big these distances differ, because on the picture they look not that different, and here they look very different. It's also not really good coloring, because if we slightly increase the color, we are not getting ever jumps from this. I mean, this is a jump from this color to this color, and then jump to this color. It's not a slight gradient, which would be way better to have. Okay, yeah, they call this Voronoi diagrams. Voronoi. Okay, if you tile all the surface by these parallelograms, then you can call this diagram Voronoi diagrams. It's absolutely not important how do you call them. It's just a famous word, famous title of these diagrams, because of some mathematics that is not relevant here. Yeah, like I didn't say, but it's obvious that this color represents distances. Okay, I'm 80% assured that I didn't miss anything useful here. Like the first two vertices are the two neighboring coordinates from which the distance that the polygon represents is calculated. The first. Yes, okay. Like I mean everything. I was just trying to make myself assured that this is nothing that I missed. So yes, like here it's written, this is the two vertices from which we calculate this polygon. I didn't tell you why do we have these two shapes. One is partially transparent, one is not transparent at all. I don't know, maybe it's commented here, but it already takes a lot of time to understand what's going on here, so it's better to just skip it. there is some idea why we have two colors. I don't understand it, and I'm assured that it's not a reasonable waste of time to go to it. So I don't want to have another stream about this article. I want to finish it, so we will go to numerical methods after the break. Yeah, so I will go to the break, little one, for like a minute, actually less. Then we will go through numerical calculations. Then we will, do what? We will discuss the experimental realizations, and it will be fast because I understand that there is no much sense to discuss everything what happens there. Anyway, nothing will be really clear and nothing will be really useful, but we need to do our job on a high quality and finally finish understanding this article. And like, anyway, like, I'm a theoretical physicist, so I'm not very much motivated to study the numerical methods and experimental part. I will just overview what happened there, which with methods, and that will be a good finish of this article. So you see that there are a lot of unclear statements and unclear explanations. That's unfortunately what's going on there, but also there are good ideas, nice overview, and results which were not published before. And that's why we spend time on this article. Okay, so let's continue and finally finish this long and complicated and a little bit abstract article. I wish it could have better explanation, but that's how science works, that not always we have enough, like, as good explanation as we would like to have. By the way, I was guessing that RS equal to 3.5 recently. No, it's 4.5. Isn't important? No, not at all. Why 4.5 is the best one, I don't remember, but there is the supplementary information which gives the different results at other RSs if you really want to have this comparison. But then there is a question which RS suits experiments better, and I'm not sure that this is explained there, but you can check if you want. I don't think it's worth it. Let's just look at the results of Monte Carlo simulations, which will be very connected to this main plot, as I announced that this is the main result of the article. Okay, so somehow they do this Monte Carlo simulations. They definitely know how to do it, because that's what a lot of people in this department of this institute is doing, where this article was developed. So they don't explain much here, but they say that there is also some excitation gap, which is the difference between excited levels and like ground state and the first excited level. They also claim that somehow using this using this energy calculation schemes, which is actually very interesting how to apply. I'm very motivated to understand what do they mean by these schemes, but somehow they get the analytical formula for the energy, and they don't comment much about Monte Carlo simulations because maybe experts in Monte Carlo simulations know very well how to do this. Let's little bit pause because they are writing something about the hopping parameter. So there is a strange statement which is better to forget, that this gap, which is which can be maybe obtained analytically because we can maybe calculate the, okay, but I mean, like, okay, we can plug some states to the formula of the energy, calculate the total energy, but then I'm not sure what we can do, what we should do to get the gap. Like if something is excited, like what do we mean by excitation here? It's a very not clear statement. So here there is the world where some gap appears somehow, because somehow from analytical considerations we can get energies not only of the ground state but also of the first excited state. I don't understand at all how this formula can give us the value of the first excited state. I mean, like we can say that, hey, like we can get some zeros or ones here inside of n, little n's, but that's the only way. Okay, I can guess we can get the difference between the ground state and the excited state. They also don't give these calculations here in the article, so we can only just guess. And this thing will give us the gap. And the gap, for some reason, can give us like hopping parameter, which can entangle states. So it's absolutely not clear. It's better to just forget it, because why the gap should be connected to the hopping parameter if we don't have any hopping parameter in the Hamiltonian, right? It makes no sense. If we don't have hopping, well, like there is a physical idea behind this model which is not written here, so we can only guess, and there definitely will be a lot of guesses. What is the real physics that gives effectively this model? So if we don't include the hopping, then we just don't include the hopping, we just don't say anything about it. That's what should be done, but here they say that yeah, that this gap somehow can give the parameter that is absent in the model. Okay, then they say that okay, I mentioned here that there is another unclear statement. So they say that there are different phases. Then they say that this strange long range order, which they haven't used ever except their abstract statements. So this long range order can be found through Fourier transform of the distribution. They also say or pair distribution function, but I don't think. Yeah, they have something in the supplemental information about the pair distribution function, but I didn't come yet to that thing because there is even now really a lot of things in this article. So that's why there are two things in these numerical methods. The first thing is the result of their Monte Carlo simulation. Second result is the Fourier transform, which gives some, well, it's claimed that it's connected to long range order, and long range order is connected to the the liquid or glass state, because in liquid there is no long-range order, in glass maybe there is, but I don't know any good formula behind this abstract statement. So that's just the thing that they state there. Then there are some topological defects, and they call that these domain walls are topological defects, right? When you look here, you immediately think topological defects. Well, I of course don't think so. Like, there are just domain walls. They have some, that's the table of contents. Yeah, they have here section about topological defects, which is very easy to open. And I was reading them a little bit, but no, I have no idea what is a topological defects. And just, I don't know, it's better even not to go to this direction. That's just the main walls. I don't know why do they write at all something about topological defense. They don't use any topology ever. And there's no doubt that triangle lattices are still strongly preferred. Yeah, okay, so let's finally look at the main result of their numerical calculations. So they say that if this little f has this value, then this is the distribution of electrons. And they have this coloring, which is, of course, a bad coloring because you don't see a slight gradient when you slightly increase the distance. And here, for example, you see a big contrast, but it's actually a very tiny contrast. But the main thing is that like this is some glassy state. This is also like glassy state. So they do some things that I don't understand, because from all this section of analytical predictions, there is no way you can get this image. Even if you were computing something, I don't know why didn't they publish the code in a readable form, but from that section nothing steams that will give us immediately something that is here in the right column. Somehow they claim, I don't know why, but they claim that this column stems from that analytical consideration, and the left column stems from Monte Carlo simulation, which is also not clear how is done, but at least we understand that there is some Monte Carlo method that we can read about. And for analytical consideration, we just need to maybe read these two cited papers and hope that it will be enough to understand it. So if we have different feelings, then we have different states. That's what is announced here, and we'll see this plot very soon here in the text. This is just a snapshot of different regions, and this is the result which they got. That's what I claim here, that you can barely distinguish differences. This thing is slightly bigger than this. It's such a little difference, but on the coloring it's written very contrast way. Also, it's not clear why this thing is okay. Maybe, yeah, okay, that brings us to this figure which I didn't want to comment, that you have a big parallelograms and little parallelograms. And there is some idea that is used here. Why do we sometimes use big parallelograms, but sometimes we use little parallelograms? No, like, sorry. It's not explained here. We could do it vice versa, actually. All right. But that's how they did it. And that there are there are these different coloring of different sizes. I would, if I were doing this research, I would do the same color of the parallelograms. And here we see a strange plot, which is a Fourier transform of some plots here. They don't provide us with the formula for it. They also said that these yellow spots are from analytical prediction, but how do they do it? Of course, maybe somehow numerically. What I wanted to say that yeah, maybe this is just a numerical error, but I don't have any code, any formula for it, so I'm not able to reproduce it myself to check that it indeed so, and I don't see any of this pattern there. But the main claim, which is here, which I'll be not going sentence by sentence because of the time, that if we have this coincidence of the intensity and analytical intensity and density of Fourier transformation, then we are having the I forgot, or long range order, or it's written somewhere here. Yeah. Look, non-magic filling cases clearly show no long-range order due to the fact that peaks of intensity are not located on the expected positions and that they are blurred compared to the sharp analytical peaks. So look, let's see again this image, which I will add also to the list of main images. So for example, here we have a 1/4. So 4 is the, do we have it? Yeah, we have it. So here there is coincidence with the yellow peaks and the black peaks. And that's also a reason why we have like long range order. They don't explain what is long range order. I don't have much experience, so I remember just general formula that there is an non-vanishing correlator, which doesn't tell me much. So this article doesn't provide us with explanation of what is long range order. So some long range order is there. And also the case for 7, for 8, 9, let's check. Okay, for 7 there's coincide, for 9 it coincides, but for 8 not so much actually. Just there is the coloring that is similar. For 5 it doesn't coincide at all, and here we see indeed that it's not a crystal state. The 5 is definitely not a magic filling. So that's the main conclusion of this plot. Why does it happen and why do we do this? It's not explained in the article, so I can't tell you much. Then finally we see this main plot of the article. They also say that here these points, they correspond to these materials, which will be shown here. But that's the main thing which I already told you. The only thing that I didn't tell is that there is this green line of the gap, which is written here on the right axis. Why is it important to have the gap? Like, no, I'm not also an expert here, I don't really know. And the point was that sometimes existence of gap coincides with the crystal structure, but sometimes it doesn't. So the gap is not really important in this plot. You can just ask someone about which role does the gap play. Of course, you can remember the article from my previous plot, from my previous stream by Sipos, where they were also bothered about Coulomb interactions, and there were some statements about the gap which was determining different regimes. They were comparing Coulomb energy and the gap, but nothing was explained there, so I propose even not to think about this theory. But here they they think about the gap. They will also provide soon a table for it. And everything is around free energy for some reason. Not, I mean, maybe that's just how they call that energy, not simply energy, but the free energy. Yeah, they also sometimes again return to this unclear statement about the first order phase transition. And I can't comment it much. They never explain phase transition between what and what. I'm also not sure if they really claim that it's there, because here it's written that if we dope the system, the first order phase transition becomes a glassy transition. So here they say that basically transition from liquid to glass is the first order. That's what they claim. Is it important? Maybe no, but if it's a phase transition, why first order? Why do we have? I mean, maybe it should be blurred somehow. Maybe there should be a region of intermediate phase, and not just such a sharp transition. But yeah, it's strange why this transition is such sharp. Is there some criteria that tells us that, hey, exactly here this parameter jumps, and that's why we have this transition exactly in this point? Okay, then supplementary information tells us something about Monte Carlo method, which I don't know, so I will not tell you anything. And some details of the Fourier transformations, which maybe, yeah, is it written, is used by Mathematica. But you need some data to plug there, and we don't have data, so we can't reproduce it. And I don't think that this little paragraph explains why at all this method is used there. And the final thing from the appendix, as far as I remember, let me check, is it from appendix or not? It's better to check once than to claim something not correct. No, it's not from appendix. That's this part is not from appendix, but the plot is from appendix. So so I wanted to start with explaining why which role at all exact diagonalization plays, because this plot has already been obtained. The analytical calculations have already, there is a claim which results analytical calculations give us. So what do we really want to do with exact diagonalization? It's not written here. They say about some claim, but it's not written which claim, so it's not clear why at all we are doing the exact diagonalization. They write that how hopping alters the charge ordering. Suddenly they want to answer this question, and for this let's look again on this model. That the model that was used before. So they rewrite it, maybe not like one interaction between all of the different states, but as the two terms, like nearest neighbors, next nearest neighbors, and then now there is a hopping, and they want to understand how does this hopping affect the physics. And then they say, let's take a little model to do some numerics. And then they make some statements which I didn't read, wasn't thinking about much. They also provide in supplementary information the plot of density correlations, which I don't know why it's needed. And it's also different from Monte Carlo simulations. Which conclusion can we draw from it? I don't know. But somewhere there in Monte Carlo simulations there were also density correlations, which were not explained before. But suddenly we see a comparison with the strange correlations which can be somehow obtained from this model with the classical Monte Carlo simulations, and they not coincide. Why they were working with this at all, it's not written here, so better not asking. Okay, we are coming finally to the end. We have understood that there is this strange analytical method, which is not clear how it gives us some results, but in the table there was a result that Monte Carlo simulation gives us this distribution, analytical consideration gives us this distribution. So there are two numerical methods, the Monte Carlo simulation and exact diagonalization. The exact diagonalization gives us some correlations which we might not need, but if you really want, you can spend like 10 minutes and trying to understand why is it needed. I propose better to forget everything about exact diagonalization because it's not connected to anything else. So these are the numerical methods, and we are coming to the one between last part of the article is the experimental realization, where we will finally see this plot in the article, but I will move it a little bit less because anyway we will see it soon. So why does it want to... Oh. Okay, so we have a nice collection of experimental results that for this material there is this fitting and there is this phase. It's very interesting to check these results from the cited papers. I think it wasn't an easy thing to get this collection. Is it really useful? Maybe no, but I think it's worth it at least once or like three maybe times to check some of the materials here. Can this theory really explain what's going on there? Because it's stated here that in this article there was STM of this material and there was this phase. Then they used this great idea which I didn't explain much. Actually, I can take advantage of my app and do just like this and not scroll. But I clicked the wrong button. I should have clicked this button. Yeah, analytical considerations. And that's the nice plot right in front of our eyes. We don't need to scroll anymore. Okay. So this is the comparison of the results. It's a big job to figure out that for all of these materials exactly this model is applicable and these phases I explained. So I need to check that it really is so, but looks like a great part of the article. Okay. Then again we have some yeah, we have it's a part of the table. There are some comments about the feelings where 1/3 is here. Okay, I don't know really why did they write it here, because yes, it's obvious from the table, all of this thing. Yeah, like I don't know, perfect polyron crystals. Maybe they just selected all of the perfect crystals to the list of them, maybe because they were bored. Okay, and finally we see this plot in the article. This, I mean, not plot, but this diagram of different phases, which I have explained already a lot of times. There is a fluence parameter. Okay, they don't explain what is fluence. I don't know what is fluence again, but yeah, this is a fun exercise to get this little f from this image. I don't know how to do it, but it's advanced understanding of the article. I don't have such advanced understanding. And here there is a lot of text, and I just want you to believe me. But let's check the original article. But not, I mean, that's what I have coincides with the article from archive. But let's look at this article. Yeah, okay, so they did this. Oh no, they didn't do this job, so I didn't understand the thing. Like, why do we have A and then A and then A? So is it a typo to have an A in all of this? Because they say like it has this material, but also have this material. Like it's different materials. Why do we have A here? Maybe it's a typo. I need to ask the author of the article. But I just wanted to say that I didn't feel that there is some important information here in the comments below this this image. Yeah, they comment how to measure, but I just don't want to be wrong, but that's what I felt, that this this is a strange text. There are a lot of text. They also have like fifth, third, fourth. Yeah, and of course that's a bad way how one should write it. So here it has 1, 2, 3, 4, 5, 6. Fortunately, I didn't put the article of like final version to archive, but the information should be the same as there. And so I don't know why are they doing this, because they already have mentioned in the caption to the figure the materials that I used there. So here this is an elaboration about the same thing that just gives some more comments. Unfortunately, I wasn't reading this part carefully. I should read again, but when I was reading it 2 times, I felt that nothing is really important written here. So let's stop on this understanding that there are just not so important comments. The important thing is this plot, which gives us intuitive understanding, and also the table, which gives us references to the materials. But it would be better if I read this again, but I remind you that I was thinking right now even more than 20 hours about this article, because I was thinking around like 18 hours, and right now there is a stream which is up to 3 hours, and it's not worth it. It's information, I don't know, which is better to just skip. It's just the thing is that there is this app which gives more motivation for me to work out everything very in detailed form. So that's why I work out it in very detailed form, and I don't want to skip some information or leave it as one that I wasn't thinking enough. So maybe I will once, just for my personal pleasure, try to understand what's written here, but I'm very suspicious. I suspect that nothing will be, nothing is important here. Okay, so we're coming, let's look again at our table of contents. Sorry, little scroll is required. So we have done numerical calculations, that's the article. Then like we discussed the model, we discussed general facts about titanium disulfide, we discussed that strange analytical idea. We discussed results of numerical methods, and at least we named them. Recently, we discussed the experimental realization, and okay, I can just click here. And finally, I get this discussion where there are also some pages which I didn't went through carefully. Maybe I didn't come yet to these pages. They continue the spirit of introduction where there are a lot of unclear statements. Let's maybe look at this one from the fact. Okay, I will read it on my own. Yeah, like, I mean, there is not so much sense to read it because anyway, nothing will be explained here. Again, some ground state somehow entangles, but right now, not even one, but some low line energy states. It's not a state, it's states. And some quantum charge liquid appears. What is a quantum charge liquid? It's not clear. Yeah, I should be from the quantum charge liquid community to understand it. And they say that if we have some hopping, then there will be some quantum charge liquids. And by the way, here in this material, where is this? Well, did I put my, yeah, that's the thing. So I wanted to say that all that model is used, they claim that this model explains this, this like image where we have a collection of STM scans, but this model doesn't have the hopping. So they don't write explicitly where this model fails. They just say, hey, we simulate it and it like works. But if it works, then why do we bother about hopping term? Maybe there shouldn't be ever a hopping. So it's important if they discuss hopping, discuss the limit of applicability of this model. Of course, we can remember this discussion from here from executive organization where they introduced the hopping. And then it's unclear what happens from the hopping. Yeah, they have, but they should have written explicitly that, hey, if we have a hopping, our predictions change this or that way. But instead of this, they somehow calculated density correlation function. And for me, it doesn't tell me anything, like some abstract plot. Of course, I didn't spend 30 hours on this article. If I have spent 30 or 40 hours, I would maybe understand it better. But common sense tells us that it's better to just go to another article, maybe to the cited article, one of the cited articles from this paper, and just remember that somehow there is some density correlation function. So to conclude, discussion is written in the spirit of introduction, where there are new citations, new ideas which are briefly stated. And now there is some tunneling. I mean, this article looks very not consistent throughout itself. But that's the discussion. So if you miss the discussion, don't think that you will miss something very important. And finally, there is the conclusion where they just repeat the same statements. But like, as we all know, we shouldn't say anything new in the conclusion, and it's not the case here. They do say something new. They say that suddenly we want to calculate the temperature where everything breaks down. Maybe suddenly they want to calculate this point on the vertical axis where this maybe or this phase breaks down. For this, they use strange formula, which makes sense, but you see, like, there is this kappa, so it's not obvious why there is this kappa. There should be a discussion of it, and they studied polarance, so I should have known it, but no, I don't know. So conclusion is again in the spirit of introduction, let's say, but didn't miss much because the conclusion is, as I said in the first 5 minutes, that these are the main results of the article. And that's all. Let's finally run through the supplementary information. So they say that if you change RS, then these are the different plots which you get. A bigger version of the plots, which are like a little bit beautiful, but I don't know yet what informative value is present in them. Maybe this is written for different RS screening, and maybe later there will be okay, I'm not sure if it's written for different RS. Let's check. No, it's just the bigger pictures of the same thing that was shown in the main plot. Yeah, RS is the same as in main plot. So I mean that the conclusion here should be that RS 4.5 should be the best RS. Like I don't see it, right? We see different texture images. So here we have even a crystalline face on different RS. Maybe RS also plays an important role for the structuring. Before in this article they said that no, it's just a parameter, it doesn't matter, but here we see that actually it does matter. It's also written here in the whole beginning. Let's open. Let's see like how comfortable it is. If you want to see the beginning, I just do like this, and it doesn't work. Okay, it opened me here. Okay, it's not fully finished app, but see like I do like this and I open already the beginning of the article, except that it's aligned not in the way where I wanted. So here they say that 13 is the magic feeling, but with this RS it's not already a magic feeling, it's already a glass state. Yeah, so the question is not about this thing, but about this thing more. I wanted to tell you something from the introduction, but I have forgot already. But okay, let it be somewhere here. Yeah. Yeah, I wanted to tell you, yeah, like basically there might be some dependence on RS. They also didn't write in the introduction the magic feeling. Okay, but at 3 it's also not like a magic feeling, right? There is a clearly dependence on RS. Yeah, okay. So nothing is explained here right now. I mean, exactly here, maybe it will be somewhere below, but right now there is nothing. So bigger, beautiful pictures, do we need them? Most likely no. Is it a waste of time to look on them? Most likely yes. Details of scaling analysis. No, I skipped scaling analysis. I can't comment much. There are some words about scaling, but they were about this plot, that if you want to they said that we will rescale this gap to fit on this plot, but no, I don't know anything about scaling here. Some strange plot which I don't want to comment. And then there is a discussion about different RS. Maybe here it's explained about the different screening radii, which is very connected to some pictures which were way before this text. Okay, if you really want to know about RS, then look this thing. I'm not sure that it will tell us something useful and important. Then they have explicit values of the gap that we see here. For example, if f is 10, then here there is the gap is 0, 0, 0. So indeed, that's a very little gap. And if we have 19, then it should be here 3. Okay, I wasn't testing it before. Gap we need to divide this by this, and only then we will get the gap. So I was too fast when I said that it works. Yeah, but this works because if we divide this by this, that's approximately the same value. Here, if we divide this by this, then we should multiply by 2, 0.6. Yeah, so that's approximately here, so that works. We don't have any errors here. But actually we see that errors are actually errors are very big. Errors are just 50% here, right? For example, for 11. So they don't know if it's there or not there. It could be actually even 0. Maybe it's a bad thing to plot the middle values without an error, especially if error is such big. Right here again, like error is 50%, like why do we need such calculation at all? But okay, that's how science works. This is the published article. If you doubt, let's check again in which journal is it published. New Journal of Physics. Okay, doesn't tell me much, but that's how it works. Okay, then there is the discussion of estimation of, oh, that's V0. Yeah, finally we don't need to calculate it. So to get this temperature, we need to use this V0. I will add it to the main text to have it right in front of me. There are also useful constants to play with this theory, the value. So it's actually a useful adding. So it should be in the theory. I will put this in the theory later, because that's the advantage of this app, that I can rewrite it, I can add comments. That's why I was creating this app at all. And I was trying to understand these topological defects. I didn't succeed. It looked, I don't even remember anything from here because it looked very not informative at all. Let's read at least one sentence. A topological defect in this case is the shift of the last 3 lattice domains with respect to one another, where 3 lattices have the same filling and chirality. So chirality is some symmetry, which I forgot, but maybe if we rotate, then it will coincide with the itself. So they connect these topological defects with domains. Why is it so? Of course, it's not explained. What is exactly topological? It's also not explained. There is no reason for us to pay much attention on it. There are some abstract statements, which I consider not really important. Yeah, I was actually thinking about this plot even like 4 months ago, but I forgot about this. When I was preparing to the stream today and yesterday, I thought that, oh, I don't know at all what happens here, but right now when I'm looking, I think that once I was approximately even understanding this. Let's check. Show stark difference between magic feeling. You see, like, the problem is that there is a new parameter which wasn't mentioned ever before in this article, the acceptance ratio. What is acceptance ratio? I forgot, maybe it's written here, but if there are some new words, then it makes even harder to understand what's going on. Let's consider them as some strange useless plots and not even understand what happens here. I also don't remember any citation or, I mean, mentioning of exactly this chapter of phase diagram. So right now I don't know how this is connected to this. Let's maybe try to understand from just the plot. So if we have filling factor 2, then we are sitting here. Then if we increase temperature, we go along this line, and it means that we go along this line. Yeah, unfortunately I forgot, but once I was thinking about it. So 2 grows, 4 grows, 5, 6 grows, 4 grows, no, does 5 grow? So 3 doesn't grow. Yeah, okay, 5 and 6, they grow, but they grow differently. So whenever acceptance ratio is, the idea is that if we look at magic feelings, then we have this big growth, but for other feelings, we don't have the big growth of this strange parameter. And also you see that this axis is very not beautiful. Instead of writing times 10 to the power minus 3, they have a lot of zeros. That's why it's written in supplementary information and no one is proposed to look at this. But that's just my perfectionism to really understand everything in the article, or at least to fix my understanding and not understanding of something in the article. Okay, then here it should also work that if we have 11, so the blue and the green should be not filling factors. 7 and 9. Okay, they are filling factors. Oh, mosquito. Okay, so and the 10 and 11, they are not filling factors. So, and also 8 is not a filling factor. So here we also see a difference. However, it's hard to draw some conclusion. Yeah, like right now, filling factors have this, how to say, heel in this strange parameter, but non-filling factors do not have. Before it was vice versa. Non-filling factors had a heel. Right, that's 2. 2 was not filling. 4 and 4 was the filling factor. I mean magic filling factor. Okay, there is maybe some guess or some attempt of guess. Let's not look at this. We don't have some strong conclusion from this. I think that's connected to the filling factors, some strange plots, which maybe once I will look again, but there is absolutely no motivation and real usage of this plot. Okay, pair distribution functions. Okay, so pair distribution function is also a thing that I wasn't thinking about, but I know that there are some experiments that do measurement of pair distribution function, and it looks like this chaos. So maybe that's already a good starting point to compare one of these materials with something that is obtained by experiments, because that's one experiment, the microscopy. Another experiment is something that measures pair distribution function, which is a correlation of some electrons at different states, as far as I remember from the definition of PDF. And they claim that this is the result based on Monte Carlo simulation. So the general conclusion is that these people really are fascinated about Monte Carlo simulations, and they can do very not trivial results. For example, that's the model. Yeah, we can criticize it in many ways and say that it's hard to derive it, but even if we got this model, it's a very not trivial way how to get from these results, so that people mastered Monte Carlo simulations and also thought a lot about such material, because as we remember, there are a lot of pages of comments, like discussion, and maybe they were sitting together and brainstorming it for a long time, what at all we know, which is at least somehow related. They imagined some quantum liquid and related it because of entanglement or potential entanglement. I wasn't motivated to read these parts of the article. Maybe we'll return to them, but again, the only motivation for me is to just make this article fully thought out. So maybe I understand something, maybe I don't understand, but at least I will be calm that finally I have thought about all the statements here. right now it's not the case, and maybe it's a bad habit because it's a waste of time to think about such statements. Yeah, okay, so let's finally conclude because that's already a really long time. So the conclusion is the following. Let's scroll through the article and also have this table of contents near us. So they claim that there are some special filling factors, like how many electrons are there per unit cell. Okay, that's not exactly this number, but it's inverse of this number. And they say that we can use some like ideas of two lattices, and we can put one on top another, and only special number of how to say, of filling factors will appear from such idea of two lattices. Why is it useful? Because based on these filling factors, we can like using these filling factors, we can use this charged lattice gas model with some Monte Carlo simulation, which they explain very briefly and only in appendix, and get this phase diagram where on y-axis we have temperature, on x-axis we have number of electrons basically, and each point corresponds to a different state. And they were thinking for some time about experiments, and they said that maybe all of them are explained. I don't remember which of them are not explained, but you can like add more electrons and get from this very symmetric state to a domain state, and then you can use your broad knowledge from introduction and discussion and give some advanced comments about the domain state. For example, if it's connected to quantum spin liquid, and you have a lot of citations here, so if you really want to know something, then you can go just to the big list of citations. Look at it, just look at it. List. If you want to know something, you are not alone. You will not know it because it would take 3 months at least to, okay, maybe even like 5 months. Even if you have this great application focus structure tool, it will take at least 3 months to understand at least 70% of cited articles. So no one will understand it, but if you really want, then you can. But also, if this application had a button to download all articles in one click, then I would do it way faster. I would even connect something here from something from that papers. But that's how it works. That this is the model. It has some simulations. It has some analytical idea about these filling factors, and then some claims about analytical results. Everything is done to explain this experiment. And also there are a lot of discussions. Yeah, like for example, this strange idea of the Fourier transform of the distribution. So they connect it with some long-range order. There are really a lot of abstract discussion of some connections with something else which looks not very related. But you have at least 5 pages of just such discussion. Yeah, about the glass paradigm, something microscopic tunneling, well, a lot of things that don't really help us to create like, you remember what was announced in the abstract? In the abstract they said that what did they say about memory devices? Yeah, see, look, second sentence of the abstract, of the whole beginning of the article, that there are all electronic memory devices. That's the goal of this work, to create memory devices, but also fundamental importance. No, it's not. It doesn't help us to create memory devices. At least I don't see anything in the article that helps. And like there is no fundamental importance. They just modeled the charged lattice gas model, which they don't really explain why it's applicable. They just give some references to some people who use this model and say like, hey, if it was used successfully, we will also use. So no great fundamental conclusions can be derived from it. We just have some comments about the glass formation and something that is written very unclear, so I can't tell you much how important this article is. So, but the conclusion is that if you take this model, if you take some advanced method of simulations, you get the phase diagram, which is very connected to the experimental observations of different materials. Okay, so yeah, finally that's the end of the stream. It was a nice stream. Fortunately, no one was interested in this topic, and I very much understand this. I would not also be interested in this topic, even if I were not doing my PhD, but I'm doing my PhD, and this topic is very relevant for my research. So it was still a great practice. I showed how this focus structure tool really helps. It's not like some abstract application for just enjoy. I mean, for just promotion, like in Instagram, there are a lot of creators who promote with some reactions that like, hey, that's up. Very, very useful, but we will never use it. We will be just promoting it. So focus structure tool is a different story. It's an app that was created by a person who was trying to understand science. Like right now, still I'm this person who is still trying to understand science, and it's developed right to increase the productivity. For example, to have buttons of downloading all articles, to have like nice structuring panel that helps easily modify the work that you're working with. Everything is on your computer, so you don't need to depend on some internet, some server, or something else. You see it's clearly a LaTeX file. You can modify everything yourself, but here is the environment that is really useful and really makes the work comfortable. Like you can work with big comfort using this structural environment and so on. And we have some ideas about AI tools, which will be in the future. So I hope that this video will see someone who is interested in this topic, and it will be useful, because for me, at least, if I watched this video before, I would save my at least 16 hours of thinking. And also you will have a true impression of the article. It's not like, hey, everything is great, everything is working, everything is a breakthrough, and then you understand that no, actually it's not a breakthrough. So here I honestly tell you what I think and what is really important, what is not important in the article. But that's how science works. They did a good job. They did some discovery and did some good overview, which might be also actually useful, but most likely no. But that's how science works. I hope I will be able to do something like this also, because it's still very, very not easy to write this article and to do these complicated simulations. But in my focus structure tool, I will also create notes, which will be way more easy to understand. That's also one of the goals of focus structure tool. So thank you for your viewing after the stream, because today there was no one on the stream because the article was too boring. I understand it. But still, it was a nice time, at least for me, and I had a really great practice. So bye bye.